Hello and welcome to New England Dynamics and Number Theory seminar. We are now in Midwest. Reynold Fregoli joins us from Ann Arbor, Michigan, and he will talk about ergodic theorems for dilates of manifolds. Welcome.
Thank you. Thanks, Dimitri, for the introduction and for inviting me. It's a pleasure to be here. So indeed, today I will talk about some versions of the ergodic theorem for dilates of manifolds. And I thought the first thing to do is to recall the classical version of the ergodic theorem to make sure that we are all on the same page. And so in the classical setup, we start with a measured space, x mu, as you can see here in the slides. Let me know if you can see, I'm trying to mark things. So if you can see my markings, that's it's a good sign. And on this measured space, we consider a measure preserving transformation T from x to x. And the classical statement of Birkhoff's ergodic theorem is that for any function f in L1, the averages of f precomposed with t many times tend to a function f star, which is t invariant. So the averages I'm talking about are here in this box. And as n tends to infinity. And this happens for almost every x. So when I write pointwise next to the statement, I mean that this convergence happens for almost every x. And since the function f star is t invariant, as a corollary, we have that if the action of t is ergodic, then f star also coincides with it must be constant. And if it's constant, it must coincide with the integral with respect to mu to the function of the function f. Okay, so any questions so far? All good? Okay, so let me know if I'm going too slow, too fast, or if anything is unclear. So this theorem can naturally be generalized to actions of bigger groups. So if you think about the point transformation T that is bijective on the space X, this is nothing but an action of the group Z on X. So basically we are averaging over the action of Z. And instead of Z, one can instead take, for example, ZD or even RD. And to explain this or to show this generalization, I will use this notation, which will be fixed throughout the talk. So the action of ZD will be generated by transformations T1, T2 up to TD, as you can see here. And the action of RD will be denoted by U sub T1 sub TD, where now I'm using lowercase t1 TD, and this is just an element of RD. And okay, so with this notation, one has the following two basically generalized versions of this ergodic theorem. In the first one, where the acting group is ZD, one averages over a big cube inside ZD centered at the origin. So basically, one takes the sum for I1 ID less than n in absolute value and averages all the values f at T1 to the I1, T2 to the I2, TD to the ID. And once again, for almost every x and for every function f in L1, these averages converge to f star of x, where f star is again a ZD invariant function. And the same is true for RD. The notation has to change a little bit, but again, one can average over a big cube in RD centered at the origin. Okay, so as you can see here, this is the statement that one gets. So 1 over 2t to the power d, and then the integral of f precomposed with ut1 td at x converges pointwise to f star of x. And this time as t tends to infinity. Okay?
Okay. So whose theorem it is now? Not Birkhoff's. Who proved
No, it's not Birkhoff's. I will explain that actually there is an even more general version of this. But yeah, actually in this form, I'm not entirely sure. One can deduce it from a statement for amenable groups in general.
from Linus-Strauss, for example?
Yeah, exactly. So this is
okay,
what.
but maybe it was known to Wiener or some people.
Yeah,
I'm just curious about the literature. Maybe somebody knows what's the right reference. Okay, never mind.
Yeah, apologies. I actually, I haven't thought about this. Yeah, should have found a reference. Okay, anyway, so more generally, one can use actually the same language to denote, basically to speak about both of these averages. And this language is as follows. So one takes the group G to be ZD or RD, and one considers the Haar measure over this group, which is in the case of ZD is nothing but the counting measure, and in the case of RD is the Lebesgue measure. So the Haar measure is basically the unique invariant measure over the group G. And one takes these averages that you see here. Okay, so basically one considers the cube -1, 1 to the power d and takes dilates of this cube. And again, one averages over dilates of this cube, and the averages are computed with respect to this measure m, which is the Haar measure. And in these averages, I will use the following notation. So G dot x is nothing but the action of G on x. And when I and when I write T dot a set, in this case, the cube -1, 1 to the power d, I just mean the dilate by a parameter T of the cube -1, 1 to the power d. And I want to ask if this notation is clear, because from now on, I will never reuse this integral notation again. I will simply use a sub t dot something of f of x. So I hope this is clear up to this point. Please let me know if this notation is not clear. Okay, so yeah, so with this notation, actually, there is an even more general of the ergodic theorem, which is the theorem that I was hinting at before, which is basically for can be stated for amenable groups. Now, okay, in this talk, I will mainly be considering actions of RD, so amenable groups are not really the focus of the talk, and I will not delve into the definitions for these groups, but basically these are groups where one can basically obtain a generalization of these averages. And there is a theorem which I call even more generalized ergodic theorem that says that if you have a Follner sequence, it doesn't matter what the Follner sequence is at this stage, inside G, then you can take averages over this Follner sequence and you obtain a similar statement for any function f in L1. So these averages converge pointwise to a function f star, which is invariant under the action of the group. And again, if the action is ergodic, this function must be constant. And this theorem is actually due to Lindenstrauss. Now, why did I mention this theorem without actually being too precise about the terminology? Because thanks to this theorem, we have a very nice consequence, a very nice corollary for RD actions, which is the following. So if instead of averaging over a dilated cube, you take some set B of positive Lebesgue measure and you consider dilates of the set B, then basically you can obtain a statement of the same type for any set of positive measure. So this is the statement that you can see in the last box here. Okay, so basically for any function f in L1 and any positive measure set b in Rd, if you average over dilates of b some function as the function f, you converge pointwise to an Rd invariant function f star as t tends to infinity. So now there is not even a sequence, the limit is the continuous limit. Okay, so this is very nice. Basically, taking cubes is not really necessary. One can take balls, one can take anything when considering this averaging process. And so the main question that basically is at the core of this talk is, okay, one can do this for any positive measure set. What happens if the set has instead Lebesgue measure 0? For example, again, let's focus on a measure preserving action of Rd on the space X mu, and let's consider M, as you can see here in the slide, a set of Lebesgue measure 0. Is it true that the averages along dilates of this set of Lebesgue measure 0 converge pointwise to an Rd invariant function for any f in L1? And it turns out that this question is actually the answer to this question is very nuanced, and we don't know, we don't have a complete answer at this stage. And the goal of this talk is actually to give basically partial answers to this underpinning question somehow. And let me start with two obvious examples. The obvious example number one is that, of course, if you take M to be a single point, there is no hope to get anything, because as soon as you take a point and you start dilating it, either your point is the, let's say, the origin, then you stay there and you're just evaluating the function at the origin, or it's a point wandering to infinity. So averaging over that really basically leads to nothing. So definitely there must be some conditions on this set M that we are considering. And another obvious example, which is an example actually where everything works, is the following. So fix some ergodic direction in your Rd action. So just an element G of Rd such that the action of G is ergodic, and take M to be the set that you see here. Okay, S times G for S between 0 and 1. This is just a segment, basically, yeah, I can draw it here. It's just a segment connecting the origin and the element G. And if you basically average along dilates of this segment, because you chose an ergodic direction, clearly you should obtain an ergodic theorem. Okay, so definitely in this case, everything works. So let's consider some examples where it's unclear if things work out. Okay, and the first interesting example is the following. So suppose that instead of, let's say, averaging over a ball, which is a positive Lebesgue measure set, you average along the shell of a ball, so SD minus 1. So by SD minus 1, I mean the D minus 1 dimensional sphere. Okay, well then it's completely unclear why you should get an ergodic theorem, but actually it turns out that in this setup we do have an ergodic theorem. And this ergodic theorem was proved by Jones and Lacey separately, basically. Jones proved it in dimension D larger or equal to 3, and Lacey in dimension 2. And this happened in 93 and then in 1995. Okay, so basically their results combined show that for every function f in LP, with p larger than this number that you see here, d over d minus 1, you have that the averages along dilates of spheres converge pointwise to an Rd invariant function. And the interesting fact about this theorem is that the bound on P that you see here is actually sharp. Okay, so if you ask for P to be exactly equal to D over D minus 1, you can find counterexamples. So you immediately see that if one wants to extend the ergodic theorem to dilates of some thin set, one needs to make several assumptions. Some assumptions on the set M itself and some other assumptions on the regularity of the test functions to which you apply the averages. And so, okay, the next question is why just the sphere? What if you take, I don't know, some other nice set? I'm not asking to work with, let's say, a fractal set, but what happens if you replace the sphere with the boundary of a hypercube, for example? And then, I mean, the intuition at least would suggest that nothing should change. And basically, the main result of today's talk says that actually a lot changes, and that if you try to average along dilates of cubes, sorry, of the boundary of, say, the unit cube, then many things go wrong. Is everything clear up to this point? I hope. Yeah, if there are any questions, I'm happy to answer. Okay, great. So let's move on. And okay, so as I was saying before, this problem of convergence of these averages mainly has three ingredients. Okay, so the first ingredient is really the shape of the set M. The second ingredient is the regularity of the function f. And the third ingredient, which actually had not appeared up to this point, but I want to introduce it now, is properties of the action of the RD action that you are considering. And basically what I want to show you today is that by playing around with these three ingredients, you can get an ergodic theorem, or you can make the ergodic theorem fail in a very spectacular way. Okay, so it's just a matter of measuring these three ingredients. Okay. So the first theorem that I want to present is a theorem by myself, Prasunna Bandi, and Dmitry Kleinbock, which was proved earlier this year. And so the hypothesis is a bit cumbersome, but I tried to highlight where these elements, the shape, the regularity, and the properties of the action appear. Okay, so the shape will be red, the regularity of f will be blue, and the properties of the action will be yellow. Okay, and the statement is as follows. So suppose that X, your measure space X mu, is not just a measure space, but it's a metric space. And suppose that the action of RD on this metric space is Lipschitz and EMAO, which means exponentially mixing of all orders. I will define what this means in a second. So this basically means very good action. Okay, so really nice action. Not just ergodic, but mixing of all orders and mixing with a rate. And suppose that M is a nice set, so a C1 submanifold of dimension between 1 and D. We excluded dimension 0, of course, because points don't work for the reason I explained before. And suppose that F is the nicest function possible. So F is smooth with compact support. Then you can show that the ergodic theorem works. So if all these three ingredients are basically the best, and somehow in their all these three hypotheses are in their strongest form, you do get an ergodic theorem. And the ergodic theorem is stated here. So these averages tend to the integral of the function. And this time I have to write integral of the function because the action is mixing, so it's ergodic, and so f star must be constant, and it's mu of f. And not just that, but actually we do get a rate of convergence in this ergodic theorem, which is possible because we have a rate of mixing. and we're talking about smooth functions. So basically, one can show that for mu almost every x, and for any positive epsilon, if the time t is large enough in terms of epsilon and the base point x, the difference between the average and the integral of f is bounded above by a polynomial in t. And this polynomial in t has a degree that's connected to the dimension of the manifold. Okay, the dimension was k, and the exponent is k over 2, which is actually intuitively very, natural, right? So the bigger the dimension of the manifold, the faster you converge. Okay, so if you take a segment, you hope to prove an ergodic theorem, you converge slowly. If you take a sphere, then you converge quickly. And yeah, so let me now quickly say a word about this exponentially mixing of all orders, which I wrote down here. Basically, it's just mixing with a rate. Okay, so for every h and for every element, for every h tuple of elements, g1, gh, and g, remember that g is just rd for us. And for every function f1, fh with compact support, smooth with compact support, you have the difference between the integral of f1 composite g1 dot product f2 composite g2 dot fh composite gh, and the product of the integrals of the f1 fh is controlled by an exponential function that depends on g1 gh. This is a very natural hypothesis. Somehow, in many actions that people like to work with, one has this type of mixing, so exponential mixing. And yeah, so when I say that the action is Lipschitz, I just mean that basically if you take two elements, G1 and G2, and you act on the same X, then basically the distance is bounded above by the distance between the G's. Okay, so I mean, just the usual notion of Lipschitz for the same base point X. Okay, so I hope the hypotheses are clear. Any questions? Okay. Great. So let me now present another result where I want to show that, okay, as soon as one of these hypotheses is somehow perturbed, things can go very wrong. Okay, and this is our next result. So this result is actually in a collaboration with Jiajun Cheng and Beinuo Guo, who are two REU students at the University of Michigan. And so again, it was proved earlier this year. And the result says the following thing. So suppose, again, that you have an RD action on a measure space X mu. And assume that the action is ergodic. So I'm dropping the mixing assumption, and aperiodic. Okay, I will define what it means that an RD action is aperiodic. So this is the assumption on the action, the yellow part. Okay, and what is the assumption on the manifold M? On the set M. Suppose that M is again a C1 manifold. I did not write this. And suppose that M contains a flat part. Okay, I will explain what it means that M contains a flat part. But for now, you just can imagine basically something like, I don't know, like this. Okay. And suppose that F this time is not necessarily regular, so not smooth, but basically can be just any essentially bounded function. So then if you allow F to be any essentially bounded function, you can find a really bad F such that not only you don't get convergence over a positive measure set, but you can find an F so bad that these averages converge to the wrong limit almost everywhere. So, so basically, the theorem, as soon as you take just an ergodic action and you drop the assumption that f is smooth, but just take an L infinity function, the theorem fails, and it fails in the worst possible way. Okay, so almost everywhere you don't get convergence. And so let me now explain what it means that the manifold M contains a flat part. This is, okay, just very basic definition. So we say that M contains a flat part if there exists an affine subspace pi over D that does not contain the origin such that M intersect pi is open in M. So basically, yeah, you can take, I don't know, this affine subspace here, and then just a little bit of the subspace is contained in M. Okay, so any submanifold of this type, when you start dilating it, will not give an ergodic theorem for functions in L infinity. So this is actually in stark contrast with the case of a sphere. So if you take a circle, everything works. But if you take a circle that is a little bit flat at some point, the ergodic theorem just fails. Any questions up to this point? Okay, great. So let me go on. Yeah, you might say, oh, but I don't know, you have two theorems, but maybe these two theorems are never really true at the same time. And actually, the goal of this slide is to show you that there are some examples where both theorems work at the same time. And the example is an example we've all worked with. Suppose that X is a quotient of the form SLDR mod gamma, where gamma is some lattice in G. G here is SLDR. Okay, so gamma is just a lattice in SLDR, and consider the action on X of the full induced by the full diagonal subgroup of SLDR. Okay, left multiplication action. And then in this case, both theorems apply. Why is that? Because the action of the full diagonal group is exponentially mixing of any order. And it's also ergodic, obviously, and aperiodic. Okay, so both theorems apply in this case. So what's the nice thing that one can say? So if you take M to be, just to answer our initial question, if you take M to be the boundary of a hypercube, the average is ATM, converge pointwise for smooth functions, but do not converge pointwise for L infinity functions.
Excuse me, Reynold. So you had this aperiodicity assumption that we discussed
Yes.
at some point. So what exactly is it?
Oh, sorry. Yeah. I forgot to explain. So an RD action is aperiodic if the set, the measure of the set of those X in X such that there exists G in RD such that Gx is equal to X is 0. So basically, if you take the points of the set of all those x's such that for some element g they are brought back to themselves, then the set has measure 0. So this doesn't happen. Basically, happens almost never. Does that make sense?
Yeah, it does. Just trying to prove that this action is aperiodic.
Yeah, you already proved it,
Which I
actually.
already did, but now I forgot the
Yes.
argument.
Yes, so the argument I think was as follows. So suppose that for some element of the diagonal group, you have that AG gamma is equal to G gamma, right?
Oh, okay.
So then basically yeah, what does this mean? Mean that G inverse A G is in gamma.
Okay.
Okay, and yeah, basically one has that in G this set has measure 0 because it's just a countable union of subvarieties, and then okay, when you project it to G mod gamma, it again has measure 0.
Okay.
That does it make sense? Yeah. Okay, so basically, yes. So the action of the diagonal group is aperiodic, and therefore, yeah, therefore, basically, both theorems apply. And another nice consequence of the fact that both theorems apply is that actually you do have a mean ergodic theorem. But for any, so basically you have convergence of the averages in LP for any P larger or equal to 1, but you do not have a pointwise ergodic theorem. And the mean ergodic theorem just follows by a density argument because it's true for smooth functions, and smooth functions are dense in LP, so the mean ergodic theorem must work. But the pointwise ergodic theorem breaks down. So yeah, this is another observation that follows from the fact that both theorems work. And okay, to conclude and to show that basically this landscape is actually much more yeah, varied than one could think, I would like to also mention this theorem of Bjorklund and Fish that was proved in 2009. And again, the setup is the same. One has an RD action of on a measure space X mu, which is measure preserving, and one takes M to be a polynomial curve not entirely contained in a proper subspace. So this excludes the previous case, if you think about it, the case where M has a flat part, because a polynomial curve can never have a flat part unless the polynomial curve is entirely contained in a proper subspace. And okay, so if M is of this type and the action is ergodic, then again you have a pointwise ergodic theorem. So it really, the shape, this shows that the shape of M really really matters basically. And yeah, future direction of all of these results combined is actually basically to understand what happens for intermediate cases. So yeah, I don't know, take a manifold that is not completely flat at some point, but maybe has a zero curvature at a given point. Does an ergodic theorem in L infinity work or not? Well, it's unclear. So one probably has to, it would be nice to figure out somehow. Okay, so any questions up to this point?
No.
Okay, great. So let's see. Sorry. Okay, so basically now, yeah, in the remainder of the talk, I would like to give you an idea of how these two theorems are proved. And yeah, I don't know if there are people who are interested in Diophantine approximation in this audience. I definitely see at least two. So yeah, it's also worthwhile mentioning that the first theorem, the one for smooth functions, has a nice applications to Diophantine approximation, but they will not be part of my talk today. Okay, so but basically one can use it to prove Hinchen type theorems of some sort. Okay, and so this is in my paper with Dmitry and Prasuna. Okay, so let me let me now try to give you an idea of how these two theorems are proved. So let me start from, maybe it's good if I recall the statement of the first theorem. So the first theorem was the following. So basically you have a metric space and an RD action, which is exponentially mixing of all orders. You have a smooth function and a C1 submanifold, which you dilate. And you want to show that the averages converge pointwise as t tends to infinity. And okay, so let me now go to the proof. Yeah, so okay, so let's fix our nice function f, which is smooth with compact support, but since I want the integral of the function to be 0, I need to add some constant to it. But the fact that I add a constant doesn't really change anything. And now let me fix some sequence of TKs, maybe, I don't know if you see it, some sequence of TKs, so times that tends to infinity. And the very natural set to consider is the following. So I call it the YT omega, which is the set of those x in x such that these averages at the point x are bigger than t to the negative omega. And basically, this is a standard strategy. One can apply Chebyshev's theorem to this set and show that the measure of the set yt omega is less than t to the 2 omega, which is the inverse of this number here squared, times the integral of the function that you have here squared over x. This is just a standard application of Chebyshev's theorem. And now if you expand your square here, you get t to the 2 omega, two integrals over dilates of the manifold M, because you have a square, and then inside the integral over x of this function. And well, basically, if you just take this integral here, well, you immediately see that it's a good integral to which one can try to apply some kind of exponential mixing. So if you have these big dilated manifold, let's draw it here, and you're taking two elements, G1 and G2, and when G1 and G2 are far apart, the integral is very small. And when G1 and G2 are very close, the integral is not very small, but that means that basically you're only looking at the diagonal of this product of the two dilated manifolds. Okay, so in general, this mixing assumption, of course, I'm simplifying here because two mixing is not enough. One needs actually to use multiple mixing because the decay that one obtains from just this simple argument is not enough. But the idea is the same. And okay, once you obtain a decay for these measures mu of the set yt omega, it's just enough to apply the Borel-Cantelli lemma. Okay, so if you apply the Borel-Cantelli lemma, you obtain convergence for almost every x, basically. And once you have, you obtain, I apologize, you obtain that this set has a full mu measure. And then, okay, since the action is Lipschitz, depending on the sequence TK that you took, you can extend this to a full limit in T instead of just the limit in TK. So I hope this is clear. Let me know if there are any questions about this. Okay, good. So then now let me try to give an idea of how to prove the second theorem. Okay, so let me just go back.
Excuse me, Reynold. So
yeah.
I didn't realize that you already going to the second theorem. Just a quick question, maybe to clarify for the audience. So all you are saying is that you have two elements, G1 and G2.
Yes.
And then, so this is two mixing, not mixing of all.
Yeah, this is two mixing, exactly. But what I'm trying to say is that the two mixing, I mean, the idea could work, but it turns out that the rate of, because, okay, what do you want to prove? You want to prove that these measures, sorry, this y should have a k here because it depends on k.
Mm-hmm.
Yeah. So you want to show that the measures of yk have a basically when you sum them, you get a finite number. Because then the complement, basically one can apply the Borel-Cantelli lemma, the easy version of the Borel-Cantelli lemma. But it turns out that two mixing is not enough here. So the rate that the rate of convergence that you get here from two mixing is not good enough. So one has to use four mixing at least.
Mm-hmm.
This is what I was trying to say. Yeah.
Yeah. Okay, so if you have four mixing, then already some result holds. You don't need all.
Yeah, exactly. Yeah. And of course, the better the mixing, the higher the order of the mixing, the better the convergence. Basically the rate of convergence between the two of the averages to the limit. And actually, this rate of convergence that we got, which was t to the k over 2 plus epsilon, is obtained by taking actually mixing of all orders. So you take the most powerful version of mixing that you can, and you basically approach this exponent. Sorry, negative k over 2 plus epsilon, where k is the dimension of the manifold. Yeah. Yeah, any more questions? Okay, great. So let me now go to the second theorem. And the second theorem, actually, one needs some intermediate results. Okay, so remember, the second theorem says the following. So you have a space X mu, which is, okay, non-atomic, and an ergodic and a periodic action of Rd. And you assume that the manifold M contains some flat part, as you can see in the picture. Then the averages converge to the wrong limit almost everywhere. This was the result. And okay, so let's try to see how one can approach this result. Okay, so basically the idea is to go back to a result which is basically classical in ergodic theory, which is that of moving averages. So instead of the usual ergodic theorem, I want to do the following thing. I have T, which is a measure preserving transformation on the space X mu, and I take two sequences of integers, nk, which can be positive or negative, and lk. And I take averages of this type. So, so 1 over lk, and then I average basically between nk and nk plus lk. So if you think about it, you have, I don't know, n1, and you average it up to n1 plus l1. Then you have n2 here, and you average up to n2 plus l2. And so on and so forth. So this is some type of averages that have been studied in the past, especially in the 90s. There was a large group of people who tried to basically treated several special cases, and eventually the definitive result on these type of moving averages was proved by Bellow, Jones, and Rosenblatt in 1990. And the result says the following. Assume that the action of T is ergodic, obviously. Then these averages converge pointwise if and only if, so they have a characterizing condition. They converge if and only if the sequence NK-LK satisfies the so-called cone condition. And what is the cone condition? I haven't written it down because it's actually easier to understand what the cone condition is through a picture. So basically one plots these numbers in R2, N1, L1, N2, L2, I don't know, N3, L3, and so on and so forth. And then takes cones, let's say of 45 degrees up above these points, and considers the section and the horizontal section of these cones. And the cone condition basically says that as you increase the height of the section, the area inside the cones should grow linearly. The part of the section contained inside the cones should grow linearly. And one can show that if this condition on the sequence NKLK, it's an elementary condition. Okay, so if this condition holds, the averages converge pointwise. If it doesn't, they don't converge pointwise. Okay, so it's a very nice result. And in fact, when the cone condition does not hold, something much, much worse happens, which is basically the result that gives us our failure of the ergodic theorem. Okay, so this theorem is again in the same paper of Bellow, Jones, and Rosenblatt. So again, suppose that T is an ergodic is a transformation that acts ergodically and aperiodically. And suppose that now the cone condition fails. If the cone condition fails, one can find sets B in X of measure of extremely small measure, such that these two things happen. So the lim_inf of AK applied to the characteristic function of B is 0, and the lim_sup of AK applied to the characteristic function of B is 1 almost everywhere. So basically, as soon as the cone condition fails, you have lim_sup 1 and lim_inf 0 almost everywhere. And this is a very strong type of failure. Okay, any questions up to this point? Okay, great. So basically, what I would like to do now is to show that in reality, this is the result that we need. Sorry. What am I doing? Yeah, this is the result that we need to prove the failure of the ergodic theorem in L infinity. Okay, so bear with me. I will come to the proof of our theorem in a second. So the next step is to take this theorem of Bellow, Jones, and Rosenblatt and to generalize it. Okay, so instead of moving averages in Z, when Z is the acting group, one takes a moving averages when RD is the acting group. Okay, and this is exactly what we did with my students. And here, actually, I would like to publicly thank Alex Gorodnik for suggesting to read this paper of Bellow, Jones, and Rosenblatt, which basically helped us very much understand like how to proceed. And okay, so what does one do in the case of RD? Basically, the situation is the same. Instead of considering segments over which you average in Z, and now one takes RD and takes boxes in RD. Okay, so one takes ergodic averages over boxes in R2 or whatever. And so basically one takes some points, WK, and lengths, SK, and consider these boxes here. BK, which are just WK1 plus SK1, WKD plus SKD, and takes the averages over those boxes, okay, which I denote by NKF. And yeah, what we prove with my two students is a similar result to what Bellow, Jones, and Rosenblatt obtained. And actually, for the case of ZD, I should mention that this result was earlier obtained by Jones and Olsen. And the result says the following. So assume that the action is ergodic and aperiodic, which I forgot to write. Okay, suppose that the action is ergodic and aperiodic, and suppose that in at least one coordinate, the cone condition fails. Okay, so you don't need it to fail in all coordinates. Suppose that in one coordinate for the sequence WKI, SKI, the cone condition fails, then you get a similar result. So basically, there is a set B of arbitrarily small measures such that almost everywhere you get this. So the lim_inf of the averages applied to the characteristic function of B is 0, and the lim_sup is 1. So basically a spectacular failure. And okay, the converse is also true. If the cone condition holds in all coordinates, you do get a pointwise ergodic theorem, but you get a pointwise ergodic theorem only for functions in LP with P strictly larger than 1. And this is a very interesting thing. So the method fails for P equal to 1, and actually one can show that in the case of ZD, at least, for P equal to 1, the theorem is just false. So this is very surprising. I'm not entirely sure why this happens, but I can just say a couple of words. So usually all these theorems are proved via maximal inequalities. Okay, so these are some strong PP type inequalities for certain operators, and in dimension P equal to 1, actually one can only get a weak 1-1 type inequality, and this weak 1-1 type inequality is actually fails in dimension in higher dimension. So yeah, this is surprising. Anyway, so now, okay, once we have this result, let's try to prove theorem 2, and the proof will be a proof by picture, basically. So let's take our space, R, let's say D equal to 2. So the space is R2. And let's consider a very simple set M. M is just the vertical segment that you see here. And then dilates of M, they just look like this. Okay. And all right, so dilates of M look like this. One, instead of taking segments, one can consider boxes. Okay, so one can take this box, then this box, then this box, this one, and so on and so forth. Well, and it turns out that if where let's say these all these sides that you see here are of length 1, and the sides that you see here are of length k, integer k, and they increase. And one can show that if one side of the boxes has fixed length equal to 1, so it doesn't increase, meaning that in that coordinate you only have average over 1 point, then the cone condition must fail in that coordinate. If the cone condition fails in that coordinate, it means that our result is applicable to averages along these boxes, averages AK. Okay, so this means that basically one can find one can find a set B such that AK average, where AK is the average along the boxes, okay, applied to KB has a lim_sup 0 and lim_sup 1 and lim_inf 0. And now, okay, how does one conclude? Well, it's enough to foliate these boxes via segments. Okay, so if averaging along all these boxes leads to lim_sup equal to 1, where there must be a segment inside the box, okay, and the average along that segment will converge, basically will have lim_sup 1. and there will be another segment such that the lim inf will be 0. And so this gives basically a subsequence of dilates along segments where the ergodic theorem fails for this function chi b. Okay, and what does one do in general? Well, okay, if you have a manifold that looks like this, it's enough to change base basically in the action and to transform this flat part into our favorite segment for which this nice proof works. Okay, so basically that's the idea of how the proof works. Yeah, so I think I'll probably stop here.
Okay, well, thanks. Let's give a round of applause, either by sending these nice pictures or real life. Any questions? We still have a few minutes for questions, comments.
I have a question. So does the flat part of M have to be, for this argument, it has to be contained in an affine subspace with a non-trivial translation part, is that right?
Yeah, absolutely. Yes. Because I mean, otherwise the theorem doesn't work, right? So if you remember, there is an example of, you take an ergodic direction, right?
Exactly.
And you dilate in that direction. Clearly, then your theorem fails in that direction, right? So it must have a non-trivial translation. Yeah.
I see.
Okay. So, is there any? Does it make sense to think about maximal ergodic theorems for those dilates?
Yeah. Okay. One can try to. Basically, what happens is that if somehow we didn't do it for dilates, but what we did was, so in this case here, so for boxes in RD, we show that if the cone condition holds in every coordinate, you do have a maximal ergodic theorem. And actually, Bellow, Jones, and Rosenblatt show that if the cone condition does not hold, you not only you don't have an ergodic theorem, you also don't have a maximal ergodic theorem. But we did not generalize. We did not generalize that part of their argument because we didn't need it actually. But my feeling is that for these segments, also the maximal inequality is false. So basically. Basically using the same argument, like if for moving averages, the maximal inequality fails as soon as this cone condition does not hold, then also for segments, which are basically a very trivial case of moving averages, where one side is just 0, right? Then it should also fail.
Yeah, okay, makes sense. What about the setup of theorem 1? If you have mixing and regular functions. By the way, I like this color coding very much.
Great. You mean a maximal inequality in that case?
Yes, some kind of maximal inequality for dilates. We haven't really thought about it.
No, I haven't tried. I never even thought about it actually. Yeah.
Okay.
But maybe it should work.
Yeah, just you mentioned maximal inequality and started.
It's definitely a possibility. Yeah. I mean, okay, to prove a maximal inequality, one can just try to apply this, all these people that worked with spheres, they prove the maximal inequality in several forms through Fourier analysis. My feeling is that one can basically try and apply the same strategy here.
Okay.
I don't have a definite feeling, but I think if the functions are very nice, the arguments, I don't know, these papers of Jones that I mentioned before and Lacey, I have a feeling that one can try to do something, yeah.
Okay. Other questions? Okay, if not, let's thank Reynold again. This was a great talk.
Thank you.
Thank you very much, and look forward to more meetings in the future.